Now, combination of resistors. There are two types of combination. One is series combination and another one is parallel combination. Now, in series combination, two or more resistors are connected in such a way that same current pass through each of the resistors. So in the diagram, we have three resistors having resistance R1, R2, and R3. These are connected in series across a potential difference V. And the current I here is flowing through the resistors R1, R2, and R3. So the same current I flows through each of these resistors. So that is one point that we need to remember in series combination, that the current is same in all the combination of the resistors. But the potential difference across the resistors, they are different. Since the resistance is different, the potential difference, which is given by Ohm's law, okay, your V is equal to IR. Since the resistance is different, the potential difference will also be different. So here the potential difference across R1 will be V1 and it is equal to IR1. And the potential difference across R2 will be V2 and it is equal to IR2. And the potential difference across R3 is V3 and that is equal to IR3. And all these potential V1, V2, V3, these are the sum. Okay, the sum of these potential will give us the total potential difference across the combination, that is V. Hence, V is equal to V1 plus V2 plus V3. And again, using Ohm's law, you can see in the equation, instead of V1, we can write IR1, V2 we can write IR2, and V3 we can write IR3. And taking common I, we have V to be equal to I, R1 plus R2 plus R3. And suppose here we have a resistance which is called an equivalent resistance, okay, which is equal to the combination of the three resistors. So instead of having three resistors, we can have, if we have one resistor, okay, which have the same resistance as the combination of these three resistors, and let that equivalent resistance be Rs, then the potential difference across that resistor, one resistor, will be IRS. And putting the value of V is equal to IRS in the equation, V is equal to IR1 plus R2 plus R3, we get IRS is equal to IR1, I into R1 plus R2 plus R3, and we cancel II, and we get Rs to be equal to R1 plus R2 plus R3. So this is the equivalent resistance, or the total resistance of the combination of the three resistors of resistance R1, R2, and R3. And since we're adding all the three resistance, the total resistance, okay, upon combining in series combination, will increase. So if you combine any resistors in series, the resistance of the combination will increase. Now in the next type of combination, we have the parallel combination. Now in this combination, the current flowing through the different resistors is different, but the potential difference across the resistors is same. So in the diagram, we have three resistors of resistance R1, R2, and R3, and you can see here that they are connected in parallel, which means that the potential difference across the ends of these resistors is V, and the current through resistor R1 is I1, resistor R2 is I2, and resistor R3 is I3. So here the current flowing through each of the resistance is different, but the potential is same. So in this combination, we shall make use we shall make use of Kirchhoff's Kirchhoff's current law, which says that the sum of current entering is equal to the sum of current leaving. So here we have I to be equal to I1 plus I2 plus I3. And again, using Ohm's law, we have I1 to be equal to V by R1, and I2 to be equal to V by R2, and I3 to be equal to V by R3. And taking common V, we have I to be equal to V. Okay, inside bracket we have 1 by R1 plus 1 by R2 plus 1 by R3. Then again here also, suppose we have one resistor which will have the same resistance as the three combination of these three resistors. Then that resistance is called the equivalent resistance of the resistors in parallel. So here is denoted by Rp, and the current flowing through this resistance will be given by V by Rp. Rp is the equivalent resistance. So we're putting this in the above equation. What we have is V by Rp to be equal to V, then inside bracket 1 by R1 plus 1 by R2 plus 1 by R3. Then cancel V. Then we have 1 by Rp to be equal to 1 by R2, 1 by R1 plus 1 by R2 plus 1 by R3. So here we can see that the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistance R1, R2 and R3. And in parallel combination, the total resistance will actually decrease. So if you combine these three resistance in this parallel combination, the resistance will actually decrease. So that is the difference between the series combination and parallel combination. Remember, in this parallel combination, V is same, current is different. In series combination, current is same, but the potential difference is different. Now we come to the concept of internal resistance, EMF, and terminal potential difference of a cell. Now, what is a cell? A cell is basically an electrical energy source which uses chemical reaction to produce voltage and current. And it actually consists of two electrodes called the anode and the cathode, and an electrolyte solution separating them. When a cell is connected in a circuit, it drives the charge in the circuit, and the rate of flow of charge is termed as current. When the current flows through the cell, its electrolyte offers resistance to the flow of current. This is because of the fact that ions have to move against the background of other ions and the neutral atoms. And this resistance offered by the electrolyte of the cell when the electric current flows through it is known as internal resistance of the cell, and it is denoted by a small letter R. Now, for a very freshly prepared cell, the value of internal resistance is very low. But as the cell is put to more and more use, its internal resistance goes on increasing. Now, when a cell is connected in a circuit, charges they flow in the circuit from the negative end of the cell to the positive terminal of the cell. The work done per unit charge by the cell to drive these charges from one end of the cell to the other end of the cell is represented by the electromotive force, or in the abbreviation EMF of the cell. Now the EMF of a cell is defined as the potential difference between the two poles of the cell in an open circuit. That is, when no current is drawn from the cell. And the diagram of the open circuit is shown in this figure. here we can see that there's no current flow, and there is no resistor which is drawing the current from this cell of EMF E. Now R is the internal resistance of the cell, and practically the internal resistance is inside the cell, but here we have to represent the internal resistance to be in series with the cell. So we see in an opened circuit, current is not drawn from the cell. But if we connect a resistor of resistance R, then a closed circuit is formed. And in this closed circuit, a current will be drawn from the cell. So a current I here in the figure is flowing in the circuit, and this current flows through the resistance R and through the internal resistance small r also. Hence, there is a current flowing in this closed circuit, and the potential difference between the two poles of the cell in the closed circuit when current is drawn from the cell is called or is known as a terminal potential difference. Now we term this as a terminal potential difference because when current is drawn from the cell, there is a potential drop across the internal resistance of a cell. Unlike in an open circuit, the current is not drawn and there's no potential drop in the internal resistance. But here, since current flows in the circuit, there is a potential drop in the internal resistance, across the internal resistance of the cell. So the potential difference decreases. The potential difference between the two terminals of the cell decreases by an amount I into small r. Hence, the terminal potential difference is defined differently as the potential difference in a closed circuit, whereas EMF is the potential difference in an open circuit, and the terminal potential difference is always less than the EMF of a cell. Now, to find the expression for the internal resistance of a cell, again we will consider the closed circuit, and here I is current. I is the current flowing through the internal resistance R and the external resistance capital R. And here the EMF is actually equal to the sum of the potential drop across the small resistance and the external resistance capital R. So here your EMF E, this is equal to IR, which is the potential drop across this internal resistance, and plus IR, which is the potential drop across the external resistance R. This is actually Kirchhoff's voltage law. We shall study about this law, okay, which states that the sum of the EMF is equal to the sum of the potential drop across the resistances in the closed circuit. So this is an application of Kirchhoff's voltage law. Okay, so here E is equal to IR plus I into capital R. So here I into capital R is known as the terminal potential difference, and that is denoted by V. So here we have E to be equal to IR plus V. Then we bring V to the left hand side, we'll get E minus V is equal to IR. Then again, cross multiplication, we'll have R is equal to E minus V divided by I. Then R is equal to E minus V. Again, I here using this Ohm's law, you have I to be equal to V by R. Or here R, the final expression, is equal to E minus V divided by V into R. So this is the expression for the internal resistance of a cell. Okay, and the point here you need to know that terminal potential difference is always less than the EMF of a cell by an amount equal to the potential drop across the internal resistance IR. So this point is always very important. You need to remember it. Now we come to another topic, which is combination of cells. Now again, just like resistors, we can have two types of combination: series combination and parallel combination. So here in the diagram, we see n number of cells connected in series, okay, one after the other. So one terminal, the negative terminal is connected to the positive terminal of one cell. Then again, the negative terminal again is connected to the positive end of the cell, and the combination is connected to an external resistance capital R, and here a current I is flowing in this closed circuit, and the equivalent diagram is shown below. So here we have Ne to be the potential difference, and Nr to be the internal resistance. Since they are in series, okay, the total internal resistance will be the sum of the individual internal resistance of each cell. And since the internal resistance is same, so we have the total internal resistance to be equal to N into small r, and capital R here is the external resistance. So here your current, again according to Ohm's law, we can apply Ohm's law here also, current to Ohm's law or Kirchhoff's voltage law. Okay, we can apply Kirchhoff voltage law also here. Your current I, this will be equal to the potential difference Ne divided by the total resistance in the closed circuit, which is capital R plus NR. So this is the current flowing in the circuit. And here we have two cases. One case is when the external resistance is very small as compared to the internal resistance. When that happens, then we'll have to neglect this capital R, the external resistance. Upon neglecting, we'll get Ne divided by Nr, and Nn cancel, and E by R, this is actually the current due to one cell. So if we have one cell connected to an external resistance, then the current flowing through that cell will be equal to E divided by small r. And then we have another case also when the external resistance is very large as compared to the total internal resistance. Then in that case, we'll have to neglect the total internal resistance. So we have I to be equal to Ne divided by R, and E by R, E divided by the resistance will give you the current due to one cell. So you'll have to keep that in mind. If we have E, then if we divide it by a resistance, we'll get the current due to one cell. And here your I in this case will be equal to N into current due to one cell. So you can see from these cases that if the external resistance is large, then the current also will be large. Okay, and here the current is maximum when R is very large as compared to the total internal resistance. So in order to have this maximum current, the cells are connected in series, and the external resistance should be greater than the total internal resistance of the cell. Now we come to another type of combination, which is parallel combination. So the figure for this parallel combination is shown, and in the figure we have m number of cells connected in parallel, and this combination is connected to or across an external resistance capital R, and I is the current flowing in this circuit. And as you can see, the total EMF of the cells between the 2 points of the resistor capital R is the same. Hence the total EMF is equal to E, which is the EMF of the individual cells. And here the total internal resistance R, since it is connected in parallel, we'll have to make use of the parallel formula for a combination of resistors in parallel. So using the formula, we have the total internal resistance R dash, okay, or the reciprocal of the total internal resistance is equal to the sum of the reciprocal of the individual internal resistances. So here 1 by R dash, this is equal to 1 by R plus 1 by R plus dot and m times, since we have m number of cells. Hence your R dash, this would be equal to R divided by m. Now the equivalent circuit for this parallel combination is shown in the figure below again. Here we have the potential difference or the EMF of the cell to be E, and I is the current flowing in this closed circuit. the internal resistance, total internal resistance is R divided by M, and the external resistance is R. So here again I, this is equal to the EMF E divided by the total resistance in the circuit, which is the sum of the external resistance R and the total internal resistance R divided by M. And upon solving this one, simplification, we have I to be equal to ME divided by MR plus R. Then again here also we have two cases. One is when the external resistance R is much larger than the internal resistance R, and in that case we neglect the internal resistance R, so we have I to be equal to ME divided by MR, and mm cancels, so we have E by R. So again here we have E, which is the EMF of one cell divided by the external resistance. So this will give you the current due to one cell. And the next case is when the external resistance is very small as compared to the internal resistance, and in that case we'll have to neglect MR, and when we neglect MR, your I will be equal to ME divided by R. And again here E by R, this will give you the current due to one cell. So here the current is equal to M times the current due to one cell. So for the current to be maximum in this parallel combination, the external resistance has to be very small, that is negligible, as compared to the internal resistance of the cell. Unlike in the series combination, where the external resistance has to be much larger than the internal resistance, in parallel combination the external resistance has to be small as compared to the internal resistance for the current to be maximum, or to draw maximum current from the cell.